Now, I want to use this above estimate, what we just looked at a few moments ago, in terms of the estimate for the remainder, to estimate the maximum error of the 6th degree Taylor polynomial approximate for e to the 1/2. And actually, I'm going to change this to the 3rd degree, only because the 6th degree, if you can do it for the 3rd degree, you can do it for the 6th. And I don't want to mess around a lot of time doing a bunch of fractions right now. That's not going to do you any good. So let's just quickly find P3 of x. I want the 3rd degree polynomial estimate for e to the 1/2. Well, actually, I'm going to find it for e to the x. So I'm going to let f of x equal e to the x. And notice that f of 0 equals e to the 0, which equals 1. So I can use that as a known point, and it's near, at least hopefully not too far, from 1/2, or e to the 1/2. So my point will be 0, 1. And just as a quick reminder, the exponential function is going to look like this. There's 0. And at 0, this is 1. At 1, this is e. So I'm looking at a half. So I'm trying to estimate that value right there. All right, so first thing I want to do is I want to find the first derivative. F prime of x equals, well, e to the x. I'm going to evaluate it at x equals 0. That equals 1. So I'm going to have a slope of 1 for my linear approximation here for my slope of the tangent line at x equals 0. So the first degree is going to look like, well, you know what, let's not do that right now. Let's just keep right on going here. Let's do the second degree. Second derivative is, again, e to the x, evaluate at x equals 0. That's also 1. So I think you can see this is going to go on and on forever. And every time it's going to be e to the x, evaluate at 0. So it's going to be 1, 1, 1, 1, 1 all the way through. So I know this 3rd degree polynomial is going to look like the known point, which is at 1, plus a slope, which is 1, times x minus 0 to the first over 1 factorial, plus 1 times x minus 0 squared over 2 factorial, plus 1 times x minus 0. Whoops, kind of ran out of room there a little bit. There's 1 times x minus 0 cubed over 3 factorial. And of course, I would never do it like this. It's centered at 0, but I would never write it like that. In reality, I would simply just do it right here. Say P3 of x equals 1 plus x squared over 2 plus x cubed over 3 factorial. And I may as well put that factorial in there, even though it is just 2. So this is my 3rd degree polynomial approximation for e to the x. Let's take a look at Maple and just look at this function and see how well it approximates it. Now, here it is. In this particular case, e to the x is actually the green one, the green curve, and my approximation is the red curve. If you're not certain of what you're looking at, just change one. If I make this a 2, whatever color curve jumps up, it was going to be my approximation. So yeah, my red one's the approximation. So this looks like it really matches quite well. So now let's get back to the idea of our maximum error. Now I know that this absolute value of this remainder polynomial is going to actually end up being less than or equal to some value m times the absolute value of x minus a to the m plus 1 over m plus 1 factorial. And here I know that a equals 0 and x equals 1/2. So what I end up with is m times the absolute value of 1/2 to the n plus 1, which actually n was 3, so n plus 1 is 4. So let's put that in as 4 over 4 factorial. Now the question is, what's this value for m? How do I come up with that guy? Well, these derivatives are constantly e to the x. So if I maximize it on the interval 0 to 1/2, it's going to be maximized at e to the 1/2. But that's what I'm trying to estimate. So again, I can't use that because I don't know that value. That's the whole point here. But I do know what e is. So looking at the curve, I know that it's monotonic and e is up here. So that's really the first value that I know that's bigger than what I'm trying to estimate. So I can use that. So I'm going to write this as as e times 1/2 to the 4th. Clearly 1/2 is positive. I don't have to worry about the absolute value over 4 factorial. So I know that my error in using this polynomial evaluated at 1/2 to approximate e to the 1/2, the error, how far I'm off, will be no more than that. And this is e times 1/2, not e to the 1/2. So let's quickly take a look at this one more time, or actually evaluate this. I want P3 of 1/2, which could be 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 cubed over 3 factorial, which is 79 over 48, or approximately 1.64583. That's far enough. Now, e to the 1/2 minus P3 of 1/2. And obviously, this is something we're doing in the calculator because I'm trying to approximate this. So in the calculator, I'm going to let it actually do it just so I can verify my error. This is going to be equal to 0.0028. Now this maximum error I'm talking about, I'm claiming is e to the 1st times 1/2 to the 4th over 4 factorial, which is approximately 0.0071. And notice that this approximated error, I shouldn't say that, it's not an approximated error, this calculated maximum error is actually bigger than the actual error when I actually calculate this thing. And when you get a calculator to make a quick comparison, e to the 1/2 will come out as being approximately 1.64872. So you can compare my approximation with the actual out to several places, and you can see that really did a nice job. And like I claimed, the maximum error is actually considerably more than the the calculated maximum error is considerably more than the actual error out 4 places. So let's quickly add one more thing to this. Let's just say I'm going to take this maximum error, I'm going to go back to e times 1/2 to the n plus 1 over n plus 1 factorial. And let's just say that I wanted to make sure that my error was no more than 0.001. So what I need is 0.001 to be less than or equal to this. Okay, how do we solve that? Answer, you don't do it directly. Literally, I will put this into a calculator, and I'll stick it in Maple here in just a second, and start estimating values of n, and keep going until I get an n that's less than or equal to, or an n that gives me a value that is actually less than or equal to this. So here you see I have the function typed in. It's going to ask me, is it a function? Yeah. And now what I'm going to do is start putting in values, say, for n. So let's say we want a third. How about the fourth? What will that do for me? And right away, I'm getting something I don't like. I mean, what's up with this? So what I need to do is go back up here to evaluate this in a decimal format so I can get it down to 0.001. All I'm going to do is put a decimal here and a decimal right there. Although I'm not sure if they're both needed. Maybe only one's needed. And then what that's going to end up doing is giving me decimal approximations. Okay, and obviously that was not right, so what I need to do is, I can see Maple's getting a little bit confused here. I need to tell it to multiply. There we go. Now let's find f of 3. And that matches much better with the 0.0071 that I had earlier, just rounded it off. So I need to make this smaller, smaller, smaller. So let's go to 4. And we're there. This is the maximum error if I go up 4 places and I want it to be less than 0.001. I think that's what I said, right? Yeah, 0.001. And it is, because the maximum error is now 0.0007, which is obviously less than 0.001. So if I wanted to increase this accuracy tremendously with this function, all I really need to do is go out and add one more term to it, which would be the fourth polynomial at 1/2, which is 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 cubed over 3 factorial. That's what we use for our estimate, plus one more term is all I actually needed for 4 over 4 factorial. And with the addition of just that one term, we really dramatically decreased our error.